a pleasure to be here. Just to correct the affiliation, our affiliation is actually also University of Zurich and ETH Zurich, so it's not only ETH Zurich. So I am going to be talking about the structure-function duality in memristive intelligent systems. So, you know, the functionality of the brain has long been postulated to be a function of its structure, right? So to say it in other words, the structure of the brain substrate is the algorithm. There's not really an algorithm that runs on top of the brain. It's really the structure of the brain that is its algorithm. And this structure is actually at different spatial scales, right? So going from synapses and neurons that have more of like a filtering functionality to dendritic arbor, which does coincidence detection and feature detection, and then all the way, of course, to neural connectivity and graphical networks, and then to cortical microcolumns and connection between brain regions. And the structure at different spatial scale also changes at different temporal scales, right? So the synaptic plasticity and neural plasticity happens more at like tens to hundreds of milliseconds, going to dendritic plasticity and structural plasticity, which goes more in the order of seconds, minutes, and hours. And then all the way to cortical microcolumns, which of course they were evolved in every evolutionary time scale. And we at the Emergent Intelligence substrate group, we're very fascinated by this structure-function relationship, and which happens at this spatial temporal time scale. And we like to build systems that form and morph themselves in electronics, right? And in electronics, one way of making a system change is through changing its resistance. And resistive memory is a very ideal element to do such thing. So I'm very lucky that there were like talks before that talked about resistive memory, and also Giacomo is going to talk, I'm sure, a lot more about this. But just for the sake of completeness, these are non-volatile memory devices, which are in the form of resistance. They usually have a top and a bottom electrode with a switching material in between. And the state of this changes by the application of an electric field across the device. The type of devices that I work with are these hafnium oxide-based devices, which are integrated in back end of the line in 130 nanometer technology. These are built in Zurich in France. And the way that these devices switch are based on the formation and resolution of a conductive filament between the top and the bottom electrode. And the geometry of this conductive filament is what dictates or determines what the final resistance is. Now, for the rest of the talk, I'm going to say how we're going to incorporate this into this hierarchical computational primitives, which are based on this brain-inspired hierarchy, and how we can incorporate this for learning and for information processing. So starting from synapses, which is like, let's say, the most mainstream type of using these devices, and we also heard from Jason and Gert this morning. So these are extensively used for this in-memory computing architectures, where the events arrive, the memory is accessed, and the sum of the product, the input and the weight that are basically held in this resistive memory are then integrated by the neurons. And when the neuron fires, then it also feeds back. It can feed back its spikes through these recurrent weights. So these can hold both feed forward and recurrent weights. And we've been building these systems, at least like small scale systems in this 130 nanometer technology. And although we don't use open source tape outs, it still takes a very long time to come back. So we have just recently been able to to get some results out of these chips. So if you look into like one, let's say, row of these architecture of this event-based crossbar, so you can see how it works is that so you have these 1T, 1R devices. So as soon as an event arrives, this transistor closes, a voltage gets applied across the device, and a current will flow into this M2 transistor, which is a function of the resistive level of the RM. So these RMs that we work with, they have about 8 levels or 3 bits. And this is measurements from a 4 kilobit array of devices. And you can see that then we can feed this into this dynamical block, which creates this EPSC with a time constant. And depending on the level of the resistance, the peak of this current changes. And then that is fed into the neuron, which then integrates this and it fires. And you can see the firing rate of the neuron is kind of a linear function of the resistance of these, or the conductance of the resistive memory. And what we can do is to then have synaptic plasticity, right? So we want to have also online learning. So we can change this in an online manner by controlling in an online manner kind of the geometry of this filament, right? Like I was saying. And the way you can do that is by controlling the amount of current that gets pushed into the device while you're programming it. So if the higher the amount of current that you push, the thicker will be the filament, and then it will be the lower the resistance. So what you can do is to kind of calculate in an online manner, well, what is the change in your conductance based on your favorite learning rule, and then calculate let's say the desired conductance, and then apply a compliance current that will take you to that conductance. And we've been designing electronic circuits that in this case we picked delta rule. So they calculate the difference between a target and between a target rate and the rate of the neuron, and then scale that to a compliance current to be applied to the device in an online manner. So you can see here some measurement from this circuit. In the x-axis, you see the error, in the y-axis, you see the compliance current, and you can see that as the error increases, you get higher and higher compliance current for programming the device. And then we can also use this. We've used this for RM-aware online learning, just at the last layer of the feed-forward. This is just an MLP. So the hidden layers are trained offline, and then they're mapped to the RM. And the last layer of the RM is trained online. But other than the synapses, these resistive memory could also be incorporated in the neurons to represent the parameters of the neurons also, right? So the neuron itself has parameters such as leak, has refractory periods such as gain. And we have designed this kind of hybrid neuron, which the ratio between this R1 and R2 here is what determines the gain, right? So the current comes to the neuron, and then depending on the ratio between R1 and R2, some part of the current goes to the neuron. And R2C1 is basically what determines the time constant of the neuron, and R3C2 is the refractory period. So basically this integrates on C and does some thresholding, and then as soon as the neuron fires, depending on this R3C2, for some time the neuron is inactive. So that's why it's the refractory period. Now, if we want to configure these parameters to see what happens to the neuron, you can see here, for example, when if you increase R2, so the time constant of the neuron increases so that its firing rate increases. If R2, for example, is in this case, it's 50 mega ohms, the neuron never fires, and then when you increase it, the neuron starts to fire. And now if we want to configure this, right, so we need to be able to switch program the resistive memory. And this is some measurements that shows the distribution of these devices for set and reset. So you can see for set, it's a more controllable mechanism. The probability of switching in the set is kind of a sigmoid function of the set voltage that you apply to it. So it's more controllable. But in the high resistive state, it's very difficult to put the device in an actual resistance. So this is the reset plot, right? So you can see this is reset and this is the high resistive state. And if you take the distribution around 1 point, you see this kind of curve, which is this is a log normal distribution. So this is a log plot, and it's a very wide distribution. So it's basically in high resistive state, a resistive memory can be thought of as a random variable, and it's very noisy. So now having this, so how can we also, let's say, implement online learning to change the parameters of the neuron itself? So neurons also go through these, what is known as intrinsic plasticity. So they kind of change their own parameters to stay within a desirable firing rate so that they are not overactive or underactive. So this is like a homeostatic plasticity mechanism. So what we have done here is that we're calculating the difference between the actual firing rate of the neuron and where its desired range of activity is. And then depending on this difference, then we treat that as like translate that to a probability of doing a set and reset cycle, so that whenever we do a set and reset, it's as if we're sampling from a different point in this distribution of RM to find new parameters for the neuron so that it stays within this good range of activity. Now we've combined this neuronal plasticity at around hundreds of milliseconds of time scale with a Hebbian learning, which is basically spike time independent plasticity at tens of milliseconds, and applied this to this kind of excitatory inhibitory network. So excitatory network is highly recurrent. It's connected to the inhibitory population for self-organization. So we applied this to this problem of sequence learning. So this the network with its dynamics has to count and predict what would be the next letter in the sequence, which is A, N, B's, and C, and then D, N, E's, and F. So in order for the network to be able to predict what is the next letter, it has to be able to count. And we see that this has a good accuracy only when both intrinsic plasticity and the synaptic plasticity are present together at these different time scales. And also we see that as the variability of this resistive memory increases, it achieves better accuracy because basically it has a larger search space for finding the better parameters for the network. This kind of goes in the direction of the discussion we had this morning that, we can kind of exploit this randomness and stochasticity for example, for search in this case. But we also know that, neurons in the brain are not point neuron models, right? So they have dendritic compartments. And also there's been a lot of discussion about how important this dendritic computation is. So not only they use spatial parameters, which is basically weights, which we all use, but they also use temporal variables, like in the form of delays. So inspired by this, let's say, dendritic compartments in the neurons, we have designed this neuron with multiple dendritic compartments. Each compartment is integrating information at a different time scale. And each compartment has a synapse, which is a complex synapse that has both a temporal variable, which is built with this RC, and a spatial parameters, which is built by this weight or R. So the way that this works is that whenever there is an event that arrives, so this node here, so the event arrives here, this node here discharges. And then when your event goes away, then it kind of charges back through this delay memristor. So you can see here like some measurements that we did after 1 year. So the event arrives here. This is the green. The capacitor kind of gets discharged here. And then we have a thresholding mechanism and a fall edge detector, which then recreates the spike that is delayed by this RC. Now, this is great, but when you want to do real-time sensory processing, which is basically what we want to do, this delay has to be long. It has to be in the order of milliseconds or so. And that means that your RM, if you want to have small capacitors, which is what you want, your RM has to be in its high resistive state. And in high resistive state, I just told you that it's super difficult to control this resistance. So you get distributions like this for RM, which is very wide. And then you end up with these kind of delay distributions that are extremely crazy. So like this is measurements from 4 dies, and each die has about, we've measured from 20 devices. So you can see that it's like kind of all over the place. So what we thought we could do is that we could kind of reset the devices, have like a distribution of delays, long distribution of delays, and then learn the weights in such a way to pick the correct delays for doing a certain computation. So we have applied this approach to this ECG anomaly detection task. Again, I'm very lucky that the background of everything I'm saying has been said today. So we've used the ECG anomaly detection task, encoded into spikes and given it to one neuron, just one neuron with 64 synapses. So this neuron just has to say if it's anomalous or normal. And you can see that it reaches like 98% accuracy when the delay is about 50 milliseconds. And that basically gives us about 2 orders of magnitude of saving in the number of resistive memory that is required compared to a recurrent network. And the reason why is because basically you don't have to, you're kind of inserting time into this feed-forward network with one neuron instead of having to keep regenerating, through recurrency to keep cycling and keeping this information in the dynamics of the network. And this also has a lot of power savings, as you can imagine, which is really the power of this dendritic computation. And then moving forward then to the highest, let's say, spatial scale that I told you, which is basically network connectivity. So as also Gert was mentioning this morning, the connectivity in the brain is very small world, right? So most of the connections are local and you have very sparse global connectivity. So it gives rise to a connectivity matrix like this, which most of the connections kind of sit in this diagonal of the matrix. If you want to translate this into a crossbar array, which I was just telling you about, most of your connections end up being unused. So you have very low memory utilization, right? So because most of the connections are just local within neighboring neurons. So in order to increase this memory utilization, what we can do is to just break up this large crossbar array into smaller crossbar arrays, which are shown here in this green squares, which are basically this dense population of neuron connections, and then have these kind of distributed routers, which are these kind of blue routers between this quote unquote small worlds, to have a better memory utilization. And this graph kind of shows that compared, so as the size of the network scales, so if your network is very small, actually it's better just to use one big crossbar array. But as the size of the network increases, then you can see that you can gain a lot of memory savings compared to a large crossbar array. So you can see here, these are also some measurements after a year. So each neuron core is basically doing the integration computation like usual, like I was showing you before. And then the router can also be built with this resistive crossbar arrays. So you can use that as like a binary switch that either lets the spike go or kind of blocks it. So it's kind of more like this mesh routing structure, routing architectures. Now we have benchmarked this on 3 problems. One is the ECG anomaly detection task, which is just the binary classification. On the speech recognition, which has 20 classes, is the spiking Heidelberg dataset. And on the half cheetah reinforcement learning motor control task. And we have compared 3 networks. So one is this usual spiking recurrent network. One is this architecture that I just explained to you, which we call the mosaic architecture, where weights are floating point 32, or when the weights are actually resistive memory. So you can see here the comparison for each task. So the red is the baseline, which is the recurrent network. The green is the mosaic with floating point 32, and the blue is mosaic with the resistive memory. And you can see that, okay, the mosaic has some hit in the accuracy, but just a little bit. And the variability, of course, increases just because of the variability of also the resistive memory. But what we have seen is that we've compared the routing power compared to a few neuromorphic systems that we had with the power of a few neuromorphic systems. And so we have scaled this to the 130 nanometer, which is where which is what we have designed our system. And you can see that, so we have done the calculation between 0 hop energy, 1 hop energy, and then the latency. So 0 hop is basically, okay, the spike just goes back to the core itself. So the 0 hop energy gain just comes because of the efficiency of the resistive memory, because it's very, you're basically applying like 200 millivolts across, a resistance, for a very low, like let's say, tens to hundreds of nanoseconds. So that's where the efficiency is coming from. But the efficiency in the 1 hop routing, which is very great. And I have to say, these are not measurements. This is just estimations, but still, where it's coming from is because, you have this distributed routers, right? And they're very small. So you have a very small crossbar memory. And of course, it's going to be very little energy when you want to hop through it. It's just a binary resistive memory. So we really like this approach, and we really think that there is a lot of potential in this exploiting small world graphs with also using resistive memory for connectivity. So I just conclude my talk here. I showed that resistive memory can be used as a knob to kind of morph these electronic systems and actually change its structure at different spatial scales, going all the way from synapse to neuron to dendrite, and then to network connectivity, and then use it for real-time sensory processing and on-chip learning. I have to acknowledge the people that I have worked with. All of the results that I have presented has been a strong collaboration with a group of Elisa Vianello and Sealetti and her students, Filippo, Simone, and Thomas, and of course, and also to collaboration with Toshiba, with Yoshifumi, and of course, Ini Giacomo for all his supports always, and Yigit, which is a very bright student that I've been lucky to work with. So thank you for attention. I just want to shamelessly announce that ICONS is going to be 1st to 3rd of August. You still have some time to submit your paper. It's going to be the deadline is the end of April, and I hope to see you again in Santa Fe, all of you. Thank you very much.